Hello again. So in this final part of our section on conditional probability, we already saw that some events can affect other events and some events don't. And if two events don't affect each other or don't affect the likelihood of each other, we say they're independent. And specifically, we say two events are independent if the occurrence of one event does not affect the occurrence of the other. If they are independent, if A and B are independent, then the conditional probabilities are just the same as the regular probabilities. If B has no effect on A, then the probability of A given B is just going to be equal to the probability of A, and the probability of B given A is just going to be the probability of B. So so if either this holds or this holds, then the events then A and B are independent. If they are not independent, then they are dependent. We say they're dependent. And if they're independent, the probability of A and B can be it's very easy to compute. We just multiply the probability of A times the probability of B. The reason for that is because this is just going to be the probability of B. So you can sometimes it can be just as simple as multiplying the probabilities, but you can only do this if they are independent, if you know ahead of time that they don't affect each other. Now we can generalize this to not just two sets or two events, but many events. Specifically, if we have these events E1 through En, we say they're independent if you take any two events and if any two events are independent. Take EI and EJ, then if I and J are not equal, then they're independent. Okay, so that's what we mean when we say a whole bunch of events are independent. And then we say the probability of all of them happening is just the product of their probabilities. The probability of E1, E2, E3, all the way up to En. The probability of all of those happening is the probability of E1 times the probability of E2, and so on, multiplied by the probability of En. So things become very simple when you have independence of events, when you're calculating probabilities. So go to page 4, example 4. We'll see a case of this. So suppose we have a biased coin in which the probability of heads is 1/3, and it's tossed 4 times. And we'd like to find what are all these probabilities. First, we should probably note that if the probability, if you toss a coin, this coin, you're either going to get heads or tails. So they're complements of each other. So if the probability of heads is 1/3, we know the probability of tails is going to be 2/3. Okay. Now, we know the outcomes of the tosses are independent of each other, or the tosses are independent of each other. So, actually, it's going to be pretty straightforward. We use the multiplication principle here. So if we just want to talk about what's the probability that the first toss is tails, and we don't care about the other tosses, well, we just care about the first toss, and the probability of tails is 2/3. And by the way, and again, 2/3 because 2/3 is 1 minus 1/3. These are complements of each other. Now, what's the probability that the first toss is a head and the second toss is a tails? Well, this is not conditional probability. This reads as first toss is heads and the second toss is tails. Well, so this is the probability of a heads and then followed by a tails. Well, the way we do that, this is the probability that the first toss is heads times the probability that the second toss is tails. Okay. Well, this probability of heads is 1/3. The probability of tails is 2/3. So this probability would be 2/9. Okay. if we wanted to find the probability that the outcome goes heads, tails, we just compute the probability that the first toss is heads times the probability that the second toss is tails times the probability that the third toss is heads times the probability the fourth toss is tails. If we multiply all these together, we get 4 divided by 81. Okay. The probability that all tosses are heads, that's the same thing as the saying that the outcome is H, 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 H. So the probability is just the probability that the first toss is heads times the probability that the second toss is heads times the probability that the third toss is heads times the probability that the fourth toss is heads. And that's going to be 1 divided by 81. If we want to compute the probability that all tosses are tails, this is the probability that we get T, 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 T. So the probability of that is the probability that the first toss is tails times the probability that the second toss is tails times the probability that the third toss is tails times the probability that the fourth toss is tails. And this is going to be 16/81. Okay, well, how do we find the probability that at least one is ahead? Do we have to write down all the possibilities we get where we get at least one head? No, we don't. Because at least one head is the complement of no heads. So this is 1 minus the probability of no heads. Okay? And no heads is there's only one way that can happen, right? Is if they're all tails. They're all tails. Okay? So, and we just computed this probability at 16/81. So this probability is 1 minus 16/81. And I think this reduces to 65/81. And then you can do the same thing here. What's the probability of at least one tail? That's 1 minus the probability of no tails. And the only way we can get no tails if we get all heads. And we know the probability of that is 1/81. So this is 1 minus 1/81, which becomes 80/81. Now we're just getting a common denominator here. Okay. Obviously you can use your calculator if you want. Then the last example, I'll let you look at this for a moment. Say if we wanted to find the probability that an African American person, if we're given the probability of an African American person in the U.S. having type O positive blood, and this should be blood here, is 47%. If we take 6 unrelated African American people selected at random, what's the probability that all 6 of them have this type of blood? Well, you want to think about this is, picking someone at random and asking them, do you have type O plus blood, or O positive blood? It's kind of like saying, in a way, it's like flipping a coin where the probability of heads is 47%. Okay? And what you sort of are basically doing is you're taking that coin and flipping it 6 times. So that's one way you can look at this. Another way you can think of is the probability that whether these people have type O blood or not. They're all independent of each other because we're told that they're taken at random. So we don't know that they're related or not. So the way we do that is we know that the probability of one person having O positive blood is 0.47. Okay. Now the probability that all 6 have O positive blood, then that would be the probability that the first has it, the second times the probability that the second person has it, times the probability that the third person has it, times the probability that the fourth person has it, times the probability that the fifth person has it, times the probability that the sixth person has it. Okay? So that's, in other words, this is 0.47 raised to the 6th power. And that turns out to be 0.011. If we round to 3 decimal places. Similarly, if none of them have type O positive blood, well, what's the probability that one person doesn't? Well, this would be the complement of having type O positive blood is not having it. So the chance of that, the probability of that would be 0.53. And how do we get that? Well, it's 1 minus 0.47 is 0.53. Okay, that's the probability of one African American not having it. Well, we have 6, so we're going to multiply these by to the 6th power as we did up here, and so 0.53 raised to the 6th power is 0.022. And then the probability of at least one having type O blood is the complement of this, right? This event and this event are complements of each other. So the probability of this is going to be 1 minus the probability of this, which is 0.022, okay, which is 0.978. Right. So, way to get comfortable with this is practice, practice, practice. Okay. And thank you for your patience, and I will see you next time.